Mathematics is often kind of a poor relation in a science faculty. Here, we're all in math. Everyone's very proud about being here.
Based on our size, we can get a huge amount done.
We have close to 300 faculty members and over 8,000 students.
We're able to accommodate a lot of different research areas.
We get to interact with people every day who know exactly what we're working on and can relate.
Whenever I have a question or one of my students have a question, there's somebody on campus who's an expert in it.
We bear the same mission. That definitely is making us stronger.
It's really a sense of culture that creates a very welcoming environment in order to prove very deep theorems.
The collaboration at Waterloo, I think, is really a strength of this university as a whole, not just in math. My grad students can take courses in any department. People will collaborate with people throughout the math faculty, but also in engineering and biology and physics. We're interested in the same kind of problem. We're coming at it from different points of view, and that's all made very easy here.
I have colleagues across the globe. It's important to take different perspectives, and in order to do that, we need to talk to people in order to integrate ideas to really come up with deep theory.
My research area is called Quantitative Risk Management, where you use mathematical and statistical tools to analyze anything related to risk. Waterloo has a long history in quantitative finance and actuarial science due to some very important people that we hired over the years, like Philip Boy, Harry Panger, Gord Valmont. We have a very strong PhD program, and we have a very strong postdoc program. Many of my PhD students are actually employed as professors in universities that are highly ranked. The emphasis that we have on this particular field is unique in North America.
My specific research area is control and also estimation. Only because of control, a lot of systems are working properly. Without control, a robot is just a pile of metal. Our bodies have a lot of blood pressure and sugar regulation. Those are all control systems. My specific research has applications to reducing vibrations in structures, particularly space structures. We study as a dynamical system, and also how can we make the system work better, right? It's got this great combination of really important applications, but also some really interesting mathematics. Having such a great concentration of the mathematical sciences is really helpful for my research.
I love that we are a large organization with lots of specializations. There's a lot of room for people who maybe are a little bit interdisciplinary or misfits, which on a good day I like to think I am. I'm in the computer graphics lab, and I got into this business with an interest of applying ideas from math to the world of art and design. Initially, I was working on applying tiling theory to recreate the art of M.C. Escher, and over time I got more involved in the underlying mathematical problems themselves having to do with tilings. These are collections of shapes that fit together to fill space with no gaps and no overlaps. I inevitably became fascinated by some of the open problems in that field, and in the last couple of years I was extraordinarily lucky because I had the opportunity to participate in the solution to one of those long-standing open problems. The collaboration that led to this discovery was unquestionably a global collaboration. So 3 countries across 2 continents, 4 collaborators working together. There's no way that we could have done the work separately.
So my research is in graph theory, which is the study of networks, and particularly I study graph coloring or graph decomposition. And networks occur everywhere, from social networks to telecommunication networks, transportation networks, now to neural networks and the rise of AI. Understanding the structure of these networks, it really enables advancements in all of these different areas where networks play a central role. Graph theory bridges computer science and pure mathematics. It brings in probability and optimization, yet it's fundamental because it's really the study of set systems, which is the basic building block of mathematics. Graph theory has a special resonance for the faculty here because we had Tut, who was one of the pioneers of the field of graph theory, many famous theorems and conjectures, and a lot of the classical theorems in graph theory have been proved by people at the University of Waterloo. We made a lot of progress on Hadwiger's conjecture, which dates from the 1940s, and we improved the best known bounds much better than anyone thought possible.
My research is in von Neumann algebras. It's a theory that was developed by von Neumann about 90 years ago to help with foundations of quantum mechanics and also for representations of groups. There's just a deep appreciation for mathematics. It allows us the freedom to maybe choose ideas or directions that might be a little bit more risky. There's a lot of students, postdocs, professors engaging with each other and vibrant seminars, just a real excitement for what's on the edge of research.
One of the advantages to our students in general, because of the size of the faculty and the number of students we have a lot of specialized courses that can't be offered at other universities. So it means they go out into the workplace very well prepared for using mathematics in solving problems and analyzing situations.